Good evening, everyone. This is Puneet from ICF, and I would be co-chairing the session on circular solutions and innovative clean energy business model. As our uh, Honorable Prime Minister mentioned in the morning session, circular economy, circular thought process has been the part of India's DNA since ages. In recent times, circular economy has followed significant growth, particularly around the petrochemical side. We are having an interesting session with the four speakers talking about different areas on the circular economy through advanced plastic recycling, chemical recycling, plastic recycling, and understanding the carbon footprint. So I would like to invite the first speaker, Mr. Deepak Sharma. He's a senior technical team leader for Nalco Water on Ecolab company, and he will be taking us through sustainability gains through advanced plastic recycling. Over to you, Mr. Deepak.
So I will take few minutes to discuss regarding the circular economy. We have been discussing on plastic recycles all over the time, and this subject has been there in the industry for quite some time now. So the topics that I will be going through would be discussing that particular aspect of circular economy, comparing the traditional way of recycling the plastics as well as the advanced recycling that is there. And over a period of time, what we have seen is we are getting those oils, or you can say synthetic crudes that are coming out from uh, the plastic recyclers. And we have done more testing on that, trying to find out what exactly was there in those oils. So I'll just go through that brief discussion on what we found out uh, on those oil samples, and what are the challenges that we see as recycling those plastics or oils going forward from here. So, all right. So, what is if you look at uh, what is there as the plastic manufacturers, most of it is coming out from the ethylene producers are coming out from the um, primary producers are from ethylene crackers. Some of it's coming out from the reactive monomers, the polymer chains, and uh, and then what happens is then why this is required, because if you look at it, the kind of way we are working in next 3 decades, plastic usage would be tripled, or you can say it would be going threefolds. And there are pressures on everybody trying to make sure that how we can reduce that plastic usage and trying to recycle it back. So the main emphasis that is coming out from the government, which are putting in regulations, they are putting in regulations and trying to put regulations with regards to plastic, single-use plastics, even for the landfilling. Consumers are getting smarter. They don't want to use single-use plastics. They want to have something ecological that is coming out from the ecological friendly products. Corporates are seeking aggressive targets for carbon neutral, and investors are asking for more ESG performance in addition to the profits. So So what do you mean by advanced chemical recycling? Now we have seen mechanical recycling. That is nothing but you have bifurcations of all the plastic that is coming out, PET, PVC, or PP, and basically you don't change the structure or the molecular structure of the polymer, and you just go on recycling. You just sort it out and then recycle it back, trying to make a smaller uh, or make it in a different manner, which can be consumed without changing the molecular structure. But if you look at chemical recycling, that is a bit different. Here you change the entire structure of the molecular weight. And we can call it polymer monomer recycling or remonomerization. And these processes have been there. And if you look at the other way of looking at it would be plastic to feedstocks. So the basic difference between monomer recycling and plastic to feedstock recycling is that in monomer recycling, basically, it's like polystyrene getting into styrene monomer. Whereas plastic to feedstock recycling, pyrolysis have been there in the industry for a long time. Either you make the finished products or you try to make it the feedstocks for cracking it up. So this is the basic difference. Bioils are being used as a feedstock to crack it further. Either you are putting up in the furnaces of a refinery or a petrochemical complexes. So now when you're trying to recycle the feedstocks which is coming out from the biooil, the basic concern is pre-sorting. Now this was the same concern that was there in the mechanical recycle. And the same thing is the concern with the chemical recycle also. So pre-sorting the recycled material is the key. If you don't recycle it properly, it would be a problem. Now, most of all the processes that I mentioned earlier would yield all these four cuts. Basically, it would be gas and the naphtha, which would be bioil, that would be used in feedstock for recycling back to your furnaces. It will also get some heavy cuts or the waxy cuts, and some of it would be a tar-like or char material that would be coming out. New processes are coming in just trying to make sure that you have lesser amounts of char or the pitch produced out from this bioil. And more or less, the industries are now going ahead and trying to add the hydrotreaters just to make sure that the contaminants are being removed, because that is one of the major concerns that people are facing right now, the contaminants that come along with the bioil. So these are the major contaminants that you will see in bioil coming out. So the major ones are the oxygenates and the chlorides. And we have also seen that some of the bioils also show signs of nylon, and this nylon is at times precipitated out while they are going through the pumps, and they can clog the pumps. So again, main key is the pre-sorting. Now, while the emphasis is on the contaminants, that's where we started off working while we got all these bioils from last 3-4 years from various plastic recyclers across the globe. So we got around, say 100 to 200 samples that were coming out from these plastic recyclers. And we started to develop a battery of tests as to which were the major concern areas for these plastic recyclers that were coming in, and what should be done to make sure that we are able to recycle these bioils back into the furnaces. So the main one was the cold flow. The pour point was one of the concerns area. Corrosion, again, with regards to high TAN and with regards to organic chlorides that were coming in. And the gum formation with regards to the fouling, oxidative fouling that was coming out. So what we have done is, based on these tests, we have redefined the new testing procedure or a spec sheet for bioil, which can be worked in for all the bioils that are coming out from the recyclers, and then can be tested and can be given as a spec for the bioils that can be recycled back either in the ethylene furnaces or in the refinery furnaces. So the challenges with the chemical recycled feedstock would be based on our existing testing. These are the 5 things that we have seen that the product stability. What we have seen is most of the bioil is olefinic in nature. So it would be having an oxidative nature. It will form gums over a period of time. Flow properties, higher pour points. Variability is, again, one of the concerns. Now, we have seen that not one batch from the same supplier of plastic recycles was the same. So it changed from batch to batch. And just to give an example, one of the batches that came out from one of the suppliers from the recyclers showed a very high percentage of sodium and chlorides. And when we checked back, we came to know that that batch contained a high amount of potato chips wrapper. So it can change from each batch. So based on this feedstock or challenges that we faced on, we have done some testing. So this is one of the examples that we have seen that based on the product stability. Now, as I said earlier, most of it is oxidative. So the gums and the sediments, if you keep it for some time, it will start forming gums, and that can settle down in the tanks, or it can settle down in the furnaces also. So we started treating it with an antioxidant, and this is based on your plastic recyclers. And it's not limited to them, because once it goes to your refinery or to an ethylene cracker, it can also form the same stuff at your tanks. So we have done the testing. We have seen that based on the results, you can see the difference over here without and with the treatment program of an antioxidants. The second thing was the cold flow behavior, which is like reducing the pour point. Normally what we have seen is the pie oils or the stat oils are having a high base point of 6 degrees C, and it leads to having a constructed flow in the pipes or in the walls or wherever there is a flow reduction in the lines. So a chemistry can be developed. I think most of you would be aware of pour point depressants. So this was one of the chemistry that was developed just to make sure that when you add it, you can bring down that pour point to less than 21 degrees or close to that. The third was the film formation. Now, one of the samples that came in was formation of the film. Now, it can be a subset of oxidative gums that have been formed. But what we have seen is even after addition of antioxidants, the film was still there. So it was something different. So this was non-oxidative route of fouling that was being formed. So the next treatment program was to make sure that we add a solvent to the system, to the samples, and try to extract that gums which have been formed in the system, in the pie oil. So that was one of the things. So overall, if you look at it, based on the experience with Nalco has, and the kind of analysis that we have done for past 2.5 years with so many samples, we can provide a complete full cycle expertise going from sorting out the material to the pie oil recovery or hydrotreater sections for the suppliers. From there to the transportation that we might be working on, going ahead with not having a pour point, with a pour point depressant. Then going to the refineries, and then to the petrochemical complexes, various chemical treatment programs that might be there with regards to stabilizer, pour point depressants, emulsion breakers, because this is just one case that is before it goes into the refinery. What we have seen is that once it goes into the refinery, we have seen very high amounts of chlorides in the overhead because the PVC was being processed as a pie oil. That led to a higher percentage of chlorides in the overhead and then led to a very high, significant amount of corrosion. So we have the learning that has come out from all these studies is that chemical recycling is still an emerging industry. We are still not getting that kind of an yield that can make a plastic recycle a viable option as of now. We are getting things in brackets, so we might be getting containers of 10 meter cube or 20 meter cube, and that can be processed in a batch-wise operation with a bleed of around 5% or 10% along with your cracker feed or along with your refinery feed. Scaling up from pilot to demonstration, we are already working in Europe, trying to scale up to the pilot scale with one of the major petrochemical giant. And the major concern is the variability from one process to another, and even from batch to batch, which is making it very difficult for us to have a set protocol for having a treatment program for this. So contaminants in the pie oil is a concern, and ethylene manufacturers are slowly working in dilute pie oils to around 5 to 10%, along with the feedstock for refinery or petrochemicals. So this has been done in the past 2-3 years' time, and we hope that the yield pattern for the plastic recycle goes up so that we can start working it out, bleeding more into the refinery and petrochemical complexes. That's all from my side. All right?
Thank you, Deepak ji. Uh, Thanks for a great session. If anyone has any questions, we can take a couple of questions. We have a couple of minutes left. Anyone, any questions? No questions. Thank you. Thank you, sir. For my next session, I want to invite Dr. Bineesh Vijayan. He's a research manager with Indian Oil Corporation Limited, and his session would be on the waste polystyrene to styrene monomer by chemical recycling. Welcome, Dr. Bineesh.
Thank you, sir. Thank you very much for your kind introduction. A very good afternoon to all of you. First of all, I would like to thank the organizers of IEW and IOCL management for giving me the opportunity to present this work. Our previous speaker, Mr. Deepak, has already explained about the importance of chemical recycling. So that makes my job a little bit simple and easier. All right. Title of my topic is Waste Polystyrene into Styrene Monomer by Chemical Recycling. This is the disclaimer slide. Starting with a very general information about the plastic waste generation in global and Indian scenario. Globally, around 353 million tons of plastics are generated. Out of that, around 9% of the plastics are recycled, and around 19% are processed in incinerator, and 50% are sent to the landfill. Remaining around 22% is left uncollected. On the other hand, if you see the Indian scenario, India generates around 9.5 million tons of waste plastics. Out of that, around 60% is recycled. So compared to globally, the Indian India recycles more than the global scenario, and 40% is left uncollected. You can see nowadays in the news or media or in social forums, there may be news like banning of single-use plastics or SUP. The term SUP is very common nowadays because the production cost for the SUP, that is very cheap. However, they require high cost for cleaning up and recycling. Let's see what is the SUP. SUP is a single-use plastic considered as a disposable plastics intended to use only once before they are thrown away and recycled. This is the classification of plastics and their benefits. The plastics are classified based upon the behavior of heat. That is the thermoplastics and thermosets. Thermoplastics are the plastics which can be softened by the application of heat or pressure. In other words, thermoset, this cannot be softened by the application of heat and pressure. Then based upon the structure, they have been classified into homopolymer and copolymer. Homopolymers are polymers in which they are made from only one type of monomers. But in case of copolymers, they are made from more than one type of monomers. And if you see any of the plastic products, you can see the resin identification code, that is the RIC. This will identify the plastic resin from which the plastics have been made. This will help in the segregation as well as the recycling of the waste. Though plastics, what makes the plastics the beneficial than other materials? Because they got some extreme versatility, lightweight in nature, extreme durability, do not rust like metals, low cost compared to other materials, then faster production rate and excellent electric properties. This is the typical composition of MSW in India. You can see around 50% of the MSW consists of organic waste and 29% consists of the construction waste. The remaining are the recyclable waste, and plastic constitutes only the 4%. This is the, if you look the state-wise contribution of the plastic waste generation, the Telangana produced the maximum plastic waste, that is around 12%, followed by Tamil Nadu, West Bengal, UP, and Karnataka. If you look the sector-wise, the plastic waste generation, the flexible packaging plastic waste are more, that is around 42%, followed by the rigid packing and the building and construction materials. It is interesting to note the type of litter we create and how much time it is used to take to regenerate, degrade. So organic wastes of paper type litters, it will take around 1 to 3 weeks. 3 weeks. Cotton clothes, it will take around 8 to 20 weeks. Wood, it will take around 10 to 15 years. Metals like tin and aluminum, it will take 100 to 500 years. When it comes to plastics, can you imagine? It will take millions of years. So it is a real threat to our ecosystem. Though I have explained about the lot of benefits of the plastics, we can see there are many disadvantages of plastics. The mainly is the landfilling, because this is highly undesirable due to the legislative pressure, and as well as we require huge area of land for disposal. Then the transportation of waste plastic to landfill. Then environmental issues due to is biodegradable in nature. Water pollution arises due to the clogging of drainage system and endanger the marine life from the plastic diet. This is the plastic waste management hierarchy. This plastic waste management hierarchy is considered to be the cornerstone of the modern plastic waste management policy. You can see the most preferred option is the prevention, followed by minimization, reuse, recycling, and energy recovery. The least preferred one is the disposal. There are different routes by which plastic management has been followed worldwide. The first one is the landfilling. As I have already explained about that, it is highly undesirable. The second one is the mechanical recycling. This is just reprocessing of the used plastic to produce a product which is a similar type of product which is having the same or less performance than the virgin material. The efforts have been already made by the polymer technologies to recover the material from the waste plastics, but which is suitable for the secondary use. But the practical experience shows that the materials which are recovered from the through the mechanical recycling lacks some inferior mechanical property as well as durability. Then next is the biological recycling. But this biological recycling is limited only to the biodegradable polymers. And the segregation of the normal plastic as well as the biodegradable plastic, that is also a difficult thing. Then next comes the thermochemical recycling. Out of that thermal recycling, that is the incineration. The energy recovery via incineration process is limited in many countries due to it will produce some dioxins of furans, and it will emit more amount of greenhouse gases. Now the state-of-art technology has been considered as the chemical recycling. That involves the pyrolysis, which aims to convert the waste plastic into fuels or chemicals. So our technology is based upon the pyrolysis process. This is the global scenario of the plastic recycling. You can see nowadays most of the waste plastics are sending to the landfill as well as processing in the incinerator. However, as per the report, around 100% plastic recycling can be realized by 2050. And if you see the blue color, that the chemical recycling, it is expected to grow exponentially in the coming future. This is the pyrolysis process. So what is pyrolysis? This is generally just heating a material in the absence of oxygen. So there are many advantages of pyrolysis process, which enables the recycling of contaminated and mixed plastic waste, reduce the landfill burden. With the pyrolysis technology, we will get 3 types of products: liquid, solid, as well as gas. The main feature of this technology is the monomer recovery, which cannot be with other technologies. It is impossible, I will tell, and it provides the true circular as well as sustainable solution. So using the pyrolysis technology, we have converted the waste polystyrene into styrene. So polystyrene are thermoplastic material which are produced from the styrene monomer, which you know it is used as a food trays, disposable cups, then packaging material for electrical appliances. Presently, India imports around 935 kt of styrene. But the interesting fact is that there is no production facility in India so far. So we have developed a catalytic pyrolysis process for converting the waste polystyrene into styrene. So the POC has been established in our pilot plant facility at IOCL R&D Center. And as per the IOCL circular economy view, the waste polystyrene, it has been recycled by the catalytic pyrolysis, which is further purified into styrene monomer. This is the nature of the pyrolysis oil, what we got from obtained from the waste polystyrene. The yield, nature, and the composition of the pyrolysis oil depends upon the quality of waste we process, as well as many processing factors. The major factor is the type of reactor we use, the nature and the properties of the catalyst we employ, the reaction temperature, catalyst to polymer ratio, pressure condition, the flow rate of the gas, and the residence time. This is the main process steps involved. The waste polystyrene is first pre-processed, and which is then allowed to undergo the catalytic pyrolysis in presence of our in-house developed catalyst to obtain the PS pyrolysis oil of styrene content around 60 to 10%, which is further distilled and purified to get styrene of purity above 99%. This is the typical product is yield for the pyrolysis of waste polystyrene. You can see the liquid yield is around 90% we got with our in-house developed catalyst, and it is much higher than the thermal pyrolysis. The solid as well as the gas yield also very less compared to that of thermal pyrolysis. This is the compositional analysis of PS pyrolysis oil. You can see the styrene content almost 70% we got with the catalytic pyrolysis, which is more than the thermal pyrolysis. And after this, this styrene has been purified to obtain the with purity more than 99%. This recycled styrene can be used for the production of the styrene-based polymers, or it can be used as a solvent in the adhesive as well as the paint industry. So thereby providing a sustainable or circular solution for the pollution created by the waste polystyrene. This is in sync with the government of India's initiative for greener or cleaner India. This slide shows the IOCL foray into the area of chemical recycling. So we have the technology for processing the waste plastic into hydrocarbon oil, monomers, chemicals, and waxes. So with this, I am concluding. IOCL is working on chemical recycling of end-of-life plastic waste in line with the vision of being leader in circular economy. Styrene monomer with purity more than 99% can be used for the production of styrene-based polymers and can also be used in paint and adhesive industry. The present invention provides a sustainable green and circular solution and is in sync with the government initiative towards greener and cleaner India. So it is the high time to act responsibly by each one of us, be a protector of environment and beat plastic pollution by reducing, reuse and recycle. Thank you. Thank you for your kind attention.
Thank you, Dr. Bineesh. That was a great presentation. We learned more about plastic recycling and what IOCL processes are. If audience have any questions for Dr. Bineesh? Thank you, sir. Question.
I can't hear.
Can someone pass on the mic?
Check. Hello.
Yes.
When you recycle the plastic, hello, you recycle the plastic. There was this component from styrene. What was the name? I forgot the name of that. Uh, yeah. So where is it in? No. Hello. Yeah. Use. What is the application?
I couldn't.
Once you recycle the plastic, what are the applications? You said hydrocarbon oil, and what were the other applications? I just lost track.
Yeah, in this case, we are recovering the monomer styrene. But if you are asking about some other plastics,
The same one, the mono.
the,
Yeah.
this styrene can be used for any other, for the same production of the same polystyrene. It can be used, or it can be used for the production of the SBR. It can be used for the production of ABS, HIPS, or it can be used as a solvent.
Okay. So what is the procedure for? There's another procedure for that.
Yeah, styrene actually usually produced by the conventional process by the dehydrogenation of ethyl benzene.
Okay.
So we have opted another route.
And and those processes environment friendly. Those processes environment friendly.
This one is
Once you recycle.
I can.
Hello. Once you recycle the plastic and convert it into a usable form, the processes involved to convert into a reusable form are they environment friendly?
Yeah, we have to tell it is a environment friendly only.
Okay.
Doctor.
Hi.
Hi.
What is the way in which a polymer, non-biodegradable polymer, is there any research on this, which is converting a non-biodegradable polymer into a biodegradable polymer? Is there any research on this? Because that's the solution. That's the end solution. Otherwise, we are going in circles, but we'll keep using it's never going out of this world, right? So I have heard of some research on this, and some students have done some kind of a prototyping of,
See,
yeah.
for the real sustainability, we have to start from the product designing itself. So if our source is on the bio material, then it can be what you are telling that our product will be also a bio. So, but as of now, if we are producing the whatever the styrene also, it is coming from the polystyrene, means fossil fuel, whatever the other things. So whatever is available right now, we have to convert into this form. But if you design in that way, that the starting material comes from a bio source, then it is possible.
That essentially means that if there is a research which converts
Yeah,
non-biopolymer into bio is a breakthrough.
Yeah.
Yeah?
Yeah.
Thank you.
Hi, Dr. Bineesh.
Yeah.
Thank you for nice presentation. Myself, Dr. Jyoti from IIP Dehradun.
Okay.
I just want to know that in which scale your process is?
Which
In which scale?
we have successfully completed our pilot plan. Pilot plan scale study.
Up to pilot plant study. Scale? In pilot plant, up to which scale? 10, 12, 5?
That is around 10 to 20 kg.
10 to 20 kg. And any byproduct which is...
Yeah,
Hello?
apart from this oil, you will be having that gas as well as the coke.
Which byproduct?
Gas as well as coke you will be having.
Okay. Thank you.
Thank you, everyone. Thank you, Dr. Bineesh.
Okay.
Now I would like to invite my next speaker, Mr. Ashish Gaurav. He's a Senior Technology Manager from KBR, and he will be talking about revolutionizing plastics recycling through KBR Hydro PRT process. Welcome, Ashish.
Hi everyone. Plastics recycling is key to a circular economy, and my presentation today will be based on KBR's Hydro PRT process, which is revolutionizing plastics recycling. I would like by starting to first introduce the process. The technology is called Hydro PRT. Hydro pertains to water. This technology is based on supercritical water, and then PRT means plastics recycling technology. We often call it the right solution for plastics recycling, and there are salient reasons why. The first one is it's a differentiated solution. While everybody else in the world is doing pyrolysis, catalytic pyrolysis, gasification, we took the initiative and introduced a differentiated process in the field of plastic recycling. The basis of this technology has been studied for over 10 years. There is a demo plant operational in Somersby, Australia, that operates at about 8 kilotons per annum of capacity. And then this technology is able to not only recycle polyolefins, but it is able to target mixed and post-consumers contaminated plastics, multi-layered films, flexible plastics, and so on. We have introduced a modular offering of this solution. So the modular execution helps with lowering the footprint and bringing in savings in schedule and cost. So so this technology is the leading solution in the market today. If you look at the licenses sold, or if you look at the capacity that has been deployed worldwide. This technology is jointly developed by two alliance partners. We introduced this technology in an alliance with our partner called Mura Technology from UK. Mura is a technology development company based out of UK who first introduced the technology from the lab scale. The table that is displayed shows all the projects worldwide. So there are two models. The first one is a licensing model through KBR, where we offer licenses for this technology, and the client can build their own plants. The second model is through an offtake contract, where Mura acts as the project developer, and they build their own projects. KBR's engineering and licensing expertise helps accelerate and de-risk scale up and delivery, modular design, and digitization. And Mura acts as operators in its own strategic geographies, where they try to build and operate plans for early revenue, acceleration of capacity, and operational learning. And here KBR is the solo engineering provider, where we provide feed and modules on these projects. So the topic of my presentation was revolutionizing plastics recycling. And there is a reason why I chose this as the topic. Advanced recycling is not something new. Pyrolysis has been studied on mixed plastic waste for over decades. But there are some key technical issues with advanced recycling, and that is why it has lagged in commercial deployment. The key technical issues are on the left slide. So feedstock quality and contamination. Feedstock differs by source and by location. There's a lot of contaminants in the feedstock which affect the quality of the oil, the operational difficulties of plastics recycling plants. So that has been a technical issue that had not been addressed so far. The second technological challenge is scalability and high efficiency. There are a lot of chemical recycling processes that do not have a very high yield, or those are not scalable. So this is another major roadblock in commercial deployment. And the third one is every plastics derived oil has certain degree of contamination that limits its use in downstream catalytic or petrochemical or refining units. So this was again a major roadblock in commercial deployment of plastics recycling technologies. So the hydro-PRD solution, the use of supercritical water addresses scalability, high yields, better thermal conductivity. The technology that we are offering today produces the most stable and cleanest plastic-derived oils on the market. That minimal upgrading is required on these oils at most scales. And this technology also has the best in sector LC and global warming reduction potential. So I made a lot of claims on the last slide, and on this slide I would like to briefly describe the reasons why. So the first one is this is a schematic. This schematic directly compares hydro-PRD to pyrolysis. So most pyrolysis processes, the feedstock that they target is mostly PEPP. The hydro-PRD process, because of the use of supercritical water, we can target more feedstocks, feedstocks with heteroatoms, and there's a reason. Pyrolysis is like a pressure cooker. You seal up your system with the feedstock. Whatever comes as the feed, that is continued in the products. So if you have heteroatoms coming in the feed, you will get those heteroatoms in the products. That will limit your offtake and that will limit your application in downstream. In hydropurity, there's a difference. Water gets in and gets out of the system, and as it leaves the system, it takes a lot of heteroatoms alongside it. The heteroatoms get attracted to the polarity of water, and they leave the system without transitioning in the final product. And that's why, for the sake, given the same feedstock, we can give you a purer oil, or if you for the same oil, we can take in a more contaminated feedstock. The second thing is hydrocarbon yield. Most pyrolysis processes, you would see about 70 to 75% liquid carbon yield. And there is a reason. The reason is production of solid carbon char. This is because most pyrolysis processes, there are issues with thermal integration, heat transfer, and so on. In the hydropurity process, the use of supercritical water. Supercritical water is water beyond its supercritical state. So it has the thermal conductivity of a liquid and the mass diffusivity of a gas. So very good heat transfer. We get a very efficient amount of cracking in less than 30 minutes. There's a single phase. Supercritical water acts like a polar hydrocarbon. So very good heat and mass transfer. We get a single phase, good cracking. So we produce minimal char. Minimal char means high liquid hydrocarbon yields. So our process, we get about 85% liquid hydrocarbon yield. Better yield means better economics, better off-take revenue, and so on. So that's a game changer. Third thing is scalability. This is one of the major constraints of plastics recycling process. Plastic melt is highly viscous, and conveying heat transfer to that melt is often an issue. So most pyrolysis reactors, when you try to scale them up, the volume increases by L cube, but the area only increases by L square. So we soon reach a size of the pyrolysis vessel where there is not enough heat transfer area for conveying the heat to the unit. Now, in our process, it's volumetric heating, single phase, direct heat contact, no convective heating. So we can scale our reactors to any size, and that leads to a lot of capex savings once you try to scale up the unit. So that is the scalability. And then, because of no production of char, we are able to be continuous, have a high on-stream time. Our systems are designed for about 90% on-stream time. So you get better production, better productivity, better revenue. And finally, because it's a high-pressure system, it aligns with modular requirements. High pressure, high temperature system. Our reactor and vessel diameters are smaller, so it aids a modular approach. Better execution, better cost, better scheduling. So all of these are game changers in our technology, and that's why I had called it revolutionizing plastics recycling. Okay, so I talked about best-in-class LCA and best-in-class greenhouse emission reduction. And that's the statement that was made by the European Commission's Joint Research Center. They are an arm of the European Union who do scientific research on different technologies. So what they did was, in February of 2023, they carried out an independent LCA study on all plastics recycling technologies. So they studied all pyrolysis technologies, they studied our technology, they studied all mechanical recycling technologies. And they found out two major conclusions. The first conclusion was that among chemical recycling technologies, the hydropurity process had a 50% lower global warming potential than peers pyrolysis technologies. And the second one, they studied all plastics recycling technologies, mechanical recycling technology included. And they found out that that hydropurity had the best in-resource use. So what does in-resource use means? It can target most polymers than any other plastics recycling technology. Like mechanical recycling is limited to very clean, PE, PP polymers. Most pyrolysis processes are limited to PE, PP polymers. But hydropurity could take in a sufficient degree of contaminants in the feed. Other polymers, PET up to a certain extent, biomass up to a certain extent, and that's why we got the best performance in this category. This is a schematic of how the technology works. So we would first start with a plastic-rich feedstock stream. That stream would also have certain amount of contamination. There is always certain amount of metals, grit, glass, fiber with plastics. So it will go through a material preparation plant. The role of the material preparation plant is to sort and clean these plastics. Once the material preparation plant delivers a sorted, cleaned, homogeneous, somewhat homogeneous stream of plastics, we send it to a series of extruders. The extruders melt and pressurize the stream. We then contact supercritical water that comes out of a supercritical water generation, and then it gets into a series of tubular reactors. Here, the water acts as molecular scissors. We break down the plastics into smaller fragments. We get a mix of hydrocarbon phase and water. We depressurize the system. Depending on client specification, we are able to separate it into certain streams. Some clients desire naphtha-only products. Some clients desire naphtha and a gas oil product. So we can specify, or we can design the distillation column to any specification as per client specs. For every 100 kilograms of plastics entering the process, we get about 85 kilograms of liquids, about 15 kilograms of gas. There is minimal char, and then the gas is separated. About 50% of the gas is required in situ to keep the supercritical water loop running. The rest gas, you can use it for fuel, or you can use it for other applications. The water is sent. The water is separated from the hydrocarbons, sent to treatment. There we have a technology where you can recycle it to spec recycle it to demin spec for keeping the supercritical water loop running, and then the liquids you can use it for your downstream or circular applications. So that was about the chemical recycling part, but the chemical reactor or the chemical conversion step is only one part of the picture. For a holistic plastics recycling process, we have to target all four facets. So we have to target waste management, getting appropriate or sufficient amount of feedstocks, material preparation, sorting these plastic waste to something that could be put in the chemical conversion unit, the chemical conversion, and then product upgrading. So we are trying to provide a complete holistic solution targeting the entire plastics recycling value chain. So KBR is offering services in material preparation, chemical conversion, which is the hydro-PRD process, and in product upgrading. So what do we do in material preparation? So material preparation means, there are a lot of plastic feedstock streams in the market, but not every feedstock stream is applicable for chemical processing. You might find a feedstock stream that is, that is a mix of a lot of polymers, but some polymers are not appropriate. Let's say PVC. So what we do is, we help our clients design these material preparation plants that help them get access to a continuous, homogeneous, sorted, clean plastic feedstock stream for the life of the plant. So do we sell this equipment? No, we do not sell the equipment, but we are connected to a wide network of key players in this stream. So we help our clients with feed analysis, developing a feed economic model, making due diligence selections on what feeds to choose, what geographies to source the feed from, and then make diligent capex and opex calculations for helping design this plant to a spec that can be integrated with a chemical conversion unit. The next thing what we offer is upgrading of hydro-PRD products. So hydro-PRD products, require minimal upgrading. On the smaller scale, let's say 20 kTA, you might not even require upgrading. But on the larger scales, 100 kTA and 150 kTA, which will be the capacity of the plants in coming years, there is upgrading required because plastics-derived oil always have some contamination from the plastic feedstocks. So we are partnered with a world-class hydroprocessing catalyst vendor, and we have an industry-leading solution for economic contaminant removal of hydro-PRD streams. So what if you are targeting large capacity plants, then we have the hydroprocessing solution for. Modular solutions for hydro-PRD. So most plastics recycling plants, that are coming up across the globe are
Ashish, I think we are run out of time. Yeah. So okay, last 30 seconds just.
Yeah, are typically small, so 20 kT or so. Modularization helps deliver schedule and cost constraints in geographies, where labor is difficult to source, labor is very expensive. The entire hydro-PRD plant could be supplied in a set of 15 modules, delivered, installed to existing, site facilities at the client site.
Thanks, Ashish. I think we are running out of
This
time.
is the first commercial demonstration plant. It opened doors and it is getting operational first quarter. And then this is the last slide. We are offering an all-encompassing solution. If you are looking for a hydro-PRD or a plastic recycling plant, come talk to us. Thank you, everyone. And that was.
Thank you, Ashish. Thanks for your time. Next, I would like to invite Mr. Siddharth Pandey from Tata Power.
Hello everyone. I believe audible? Okay. So myself Siddharth Pandey from Tata Power Trading Company. And today the topic of discussion here is BESS as an alternative to diesel generator. Now we had been present, okay, just one second. Okay, so quickly deep diving into the scenarios, we had been present since last 75 years into power sector, and with the modus of operandi that expensive energy, just say Tata to it, we tried to innovate the solution in such a way that we come across to the grassroots users. Now, as we see in this particular slide, that in the Indo-Gangetic belt, we observed that most of the states do have somewhere around 19.9 hours of energy available. In that sense, as we see, the rural belt in Uttar Pradesh, Jharkhand, Bihar, Haryana, Punjab, these are the places wherein the energy in the rural belt is not available beyond 16 hours. Also, we observed that this is the same belt wherein the AQI is being observed as, in the most harsh segment. And the reason for that particular thing is the construction activities, waste burning, transport, DG sets, industrial, pollution emitting industries, and the domestic cooking. Now, out of this, we chose DG set replacement as a challenge. And we did work around with various farmers and small-scale industries to choose and replace their DG under our microgrid program. Along with that, as we move forward, we found that somewhere around 90 gigawatt of diesel generators are installed behind the meter, out of which somewhere around 3,000 crores of business potential we identified. Moving forward, we also understood that there had been several restrictions laid by various governing agencies for the usage of DG, wherein recently we observed that DGs up till 800 kilowatt were asked to either be retrofitted or shift towards PNG. Now, as we were discussing earlier, these were the notifications wherein the National Framework for Promoting Energy Storage Systems 2023 clearly stated that the alternative usage that the industry shall endeavor to shift to a cleaner technology such as renewable energy or BESS. Now, this was the place wherein we stepped up. And as we say that when we bring BESS behind the meter or within the premise of the consumer, there are certain benefits to the national grid overall. When BESS is placed behind the meter, definitely the consumer gets an advantage of backup power, increased PV self-consumption, demand charge reduction, and TOD bill management. Now, apart from this, the other services such as voltage correction, which in the northern states is a bigger problem, and black start are also being addressed. Unlike the other methods wherein when the BESS is placed at a larger scale in the central transmission or state transmission network or the distribution company's network. Now, as the BESS is placed with the distribution company's network, the other 4 services are missed out. So this becomes the most suitable avenue, behind the meter setup, it becomes the most suitable avenue to place a battery energy storage solution system and replace the DG overall. Now, with this, there were actually 4 technologies available for us to observe. And depending upon the use case, we chose the technologies. Most commonly used one are lithium-ion and lead-acid batteries. And recently, we also did shift towards flow batteries. Now, flow batteries do offer a higher inductive, a higher inrush current capacity and a longer duration of service. So in that case, the LCOS, levelized cost of storage for flow batteries, gets drastically reduced. Unlike the other two, wherein lithium-ion serves primarily for 10 years and lead-acid primarily for 5 years, the LCOS ranges between 17 rupees. And that's how the case combination of these batteries did come into picture. Now, as we move into the CNI segment further, definitely the flow batteries become more prominent in terms of usage. Any questions? A bit louder, please. Advantage and disadvantage as compared to DG. Now, see, DG directly is amounting to emission of the PM 2.5 and 10, right? Whereas the batteries do not, in terms of recycling, when I say flow batteries are 100% recyclable, accountable methods in case of, let's say, lithium ion, we had been using the second life batteries in our transmission receiving substations as well in Tata Power Mumbai substations. So yes, the recycling is available in terms of flow batteries as well as lithium ion. And once they are we are able to recycle them, definitely the emission norms are being curtailed, are being addressed, as we say, when the DG is being replaced. Much lesser in terms of economics. If we say, see, roughly when we say a 200 kVA range between 40 kVA to 200 kVA DG set, the generation cost ranges between 27 rupees to 33 rupees. Right? Per liter, a DG may generate between 3.3 units to 2.7 units. So the generation cost from a diesel generator ranges from 27 to 33. Now, as compared to it, LCOS for flow batteries ranges between 16 rupees. Now, this is levelized cost of storage, the energy discharge rate, right? And for lithium ion, it ranges between 19 rupees. Since the capacity will be higher and there is a degradation in lithium ion as well. Now, also if we consider the charging energy, the energy being used to charge the battery, let's say at the discom tariff of 8 rupees, yes, the batteries are comparable to 27 and 33. The moment we club the entire thing with solar, yes, there is somewhere around 2 to 2.5 rupees per unit savings observed by the customer. And that is how we are able to scale the model from the small scale industries to MSMEs and now the CNI segment as well.
Thank you. Thanks, Siddharth. I think next questions we can take offline for the interest of time.
Yeah.
Thank you.
Okay. Thank you very much.
For the next speaker, I would like to invite Sweta Kumari. She's Manager Biofuels Projects from HPCL.
Good evening, everyone. The topic of today's presentation is Understanding Carbon Footprint in Biofuel Production, and myself is Sweta Kumari, and I'm representing HPCL. Sorry. So moving ahead with the agenda, first we'll be capturing the Government of India Trust on enhancing the energy security, followed by the biofuel portfolio of HPCL and a case study that has been done on a biomass to ethanol plant. And after that, we'll be capturing the future prospects and challenges along with the proposed policy and intervention along with the conclusion. So what is energy security? Energy security is nothing but the continuous supply of energy at a very low cost, thus ensuring the reliability for the nation's economy and infrastructure. Some of the sustainable goals that Government of India has taken care is utilization of sustainable and clean energy development, by utilizing technologies that use less energy, increase energy efficiency, and shift towards renewable energy resources like hydro, solar, wind, and biomass energy. The key area, sorry, the key areas where Government of India has emphasized its efforts are the electric mobility by launching the schemes like FAME, NEMMP, and GST reduction, etc. The ethanol blending, that is the blending of ethanol of 20% by 2025. The gas-based economy, that is the launching the city gas distribution projects to for proposing the LNG and PNG sectors in the uh, commercial and in industrial use, and hydrogen economy, that is the green hydrogen mission, that the national hydrogen mission that government has launched for production of green hydrogen from the renewable resources. So, speaking about the biofuel portfolio, in line with the Government of India emphasis, HPCL is also setting up multiple biofuel plants, which includes the second generation ethanol biorefinery at Batanda, CBG plants at multiple locations, 1G plants, and biodiesel plants. So actually, what is biofuels? Biofuels are nothing but carbon neutral fuels which have low carbon footprint and which has less uh, less global warming potential. So let us understand the importance of biofuels. Biofuels are derived from the organic materials such as plants, crops, and waste, making it a renewable energy resource. And they have a balanced carbon cycle, meaning when they are burnt, they release neutral to no carbon in the atmosphere. They also emit fewer greenhouse gas emissions and are also resilient to fluctuation in fossil fuels prices and supply. They have the flexibility to be blended, which makes them more feasible option. And it also provides economic opportunities for farmers in rural communities. Hence, sustainable and responsible biofuel production practices are crucial for achieving any long-term environmental and social benefits. So understanding the carbon footprint in biofuel production is very important. Carbon footprint is measured in terms of carbon dioxide equivalent, and main components contributing to the carbon footprint in the biofuel production are the processes stage that are involved, which includes the first stage of biomass production, that is the cultivation, which includes use of harvesters and other equipments, uh, which is followed by the storage and handling, that is use of the trailers and trolleys to the processing units. The processing units also, during the processing and the conversion of biofuels, there are multiple chemicals involved, which also add to the global warming potential of the ethanol or any other biofuels. Hence, reducing the biofuel carbon footprint is very important, and the same can be done by sustainable practices and optimizing production processes and by utilizing advanced technologies. Moving ahead, carbon footprint and global warming, they go hand in hand. What is global warming potential? It is nothing but a measure of how much heat a greenhouse gas traps in the atmosphere over a specific time period, that is usually 100 years, compared to the carbon dioxide. And the global warming potential of various biofuels depends on the various factors, which includes the type of feedstock being used for the production, the process that is utilized for the production, and the specific greenhouse gas emissions associated with each biofuel. As already emphasized, the global warming potential of any biofuels depend on the feedstock that is being utilized for the production process. Hence, if we see the three types of ethanol that is being utilized in India, the ethanol based on sugars is around 15 to 30 gram of CO2 equivalent of GWP. The corn-based ethanol has a GWP of 30 to 60 gram, and the least being the biomass-based ethanol, that is 10 to 30 gram of CO2 per mega equivalent. Moving ahead to the palm oil-based biodiesel had 40 to 80 gram of CO2 equivalent per megajoule, and the UCO-based biodiesel 15 to 30. The least being the biogas, which is being produced by the digestion process. The GWP of biogas or the methane is 15 to 25 gram of CO2 per equivalent megajoule. So minimizing the global warming potential is crucial for sustainable biofuel production. So here we have done a case study of a typical biomass-based ethanol plant, and we have tried to utilize the cradle-to-grave assessment for doing the study. So in the LCA that we have done, the major contributor of GWP of ethanol comes due to chemical that is being utilized in the production process. The second being the feedstock handling, and the third being electricity, followed by the other small contributors. So understanding the chemical utilization, this is a very nascent stage, and R&D work is required to explore and develop the technologies to reduce and eliminate the need of chemicals. However, we will be talking about the next two contributors, that is the feedstock handling and the electricity being used. So the feedstock handling can be further divided into two process stages. First is the loading and unloading of the biomass or the feedstock. The second is the transportation. The loading and unloading contributes to about 23% of the total GWP of ethanol. In the loading and unloading process, major factors are the harvesters and the loaders that are being utilized for the loading and unloading process. So this use can be minimized, and GW can be minimized in case if we propose manual loading and unloading, which is being followed in India, which this also increases the employment in India and reduces GHG emissions. The second is the moisture content in the biomass. So in India, we are actually cutting the biomass and leaving it for a day or two before we bale it. Hence, this reduces the moisture content in the biomass, and hence baling and density is reduced, thus reducing the transportation cost and the transportation volume for the biomass. The second factor is the transportation, that is 77% contribution in the ethanol GWP. So this can be eliminated by following a hub and spoke model, in which we have, in our biorefinery, have tried to locate the biomass storage areas nearby to the biorefineries, so that the transportation distance is reduced, thus reducing the GHG emissions from the tractor trolleys that are being utilized for the transportations. One of the way forward that I would like to propose is using alternate fuels for transportation of these vehicles, such as biofuels or electricity, to reduce the carbon footprint of the transport during the transportation phase. If this alternative fuels are used, then we can reduce the GHG emission by 80%. The next stage is the electricity that is being used for the generation of the biofuels. So a typical any biofuel plant is utilizing coal-based power, which has a GWP of around 280 gram of CO2 equivalent per megajoule. If instead of using the coal-based power, we move ahead and we use the solar or the wind-based power for these projects, there will be a considerable reduction of these GWP. It will be around 89 to 90%, and HPCL is already exploring to set up green power, that is the wind and solar power, nearby the refinery, so that the GWP of the ethanol can be reduced. So future prospects and challenges. Apart from the 2G plants, there are multiple CBG plants that are being proposed by the government, and there is already a mega target of production of 5,000 plants, CBG plants in the Satat scheme, and already in the recent conference, there's a target of setting of 15,000 tons per day of CBG by 2026 has been set by Government of India. So understanding the CBG and the ethanol productions are almost similar. Even the CBG per ton of CBG production requires around 2,000 to 2,200 kilowatt hour of power. And if this power is being sourced from the renewable energy, then the contribution of electricity towards GWP is highly reduced, and hence GWP of the biogas can also be reduced. The last but the very important proposed policy intervention that I would like to add here. See, all the biofuel plants are treated as industrial connections, and there are fixed energy charges which are levied for these plants. Hence, as we all know, these biofuel plants are dependent on the type of feedstock and its availability. So I would like to propose that these biofuel plants are given an option of flexi connection, so that there is a boost and there is a promotion of setting up green fuel production. Secondly, the government should also try and mandate the use of green power for these biofuel plants to lower the GWP.